Hey guys, here's our chapter 3 video for this section. I am at the bottom of page 6, FYI, so scroll to section 3.2 and then go to the bottom of page 6. That's where this problem is. It's not like headed very well, so you have to hunt for it for a second. But what we're doing here is we have a problem about cars, and it's miles driven and price of the car. So as you know, the more miles that are on the car, the price goes down because that means the car has been used more, it is older. And so what we have first, and this part should be review, is what we're trying to do is interpret, identify the slope and the y-intercept and interpret. So remember that interpret word is really important. As you can see here, our slope is negative 86.18. Our y-intercept when I plug in 0 for x is just 18,773. And so those are the two key numbers that you're looking for any y equals mx plus b equation. And then what I'm going to do is write them out and do the interpretation as well. So what I've got here is our slope. Remember that the slope is always the number that's with the x variable. So this number here, the negative 86.18, is our slope. And what that means in the interpretation, you guys read about this and you wrote in the reading guide about it, is that means as you increase the x value by 1 unit, and so what's tricky about this one is that look at our x-axis down here, the x values represent miles driven. So for each additional, and I put 1,000 miles driven because these x values are in thousands. So just make sure that your units are matching up and you're using context. You're not just saying for every x value, you're saying what the x values represent. For each additional 1,000 miles driven, we expect, this word is very important to have in your slope interpretation because we don't know for sure, these are predictions. We expect the price of the car, which is the y value. 2, this should be either increase or decrease, and it is decrease in this case because our slope is negative, and you can see that the line is decreasing. And we can expect the price of the car to decrease by about whatever this number actually is. So it's kind of a fill-in-the-blank sentence. For each additional, what are the x values? We expect, make sure you have that, whatever the y value is, what it represents. This word is increase or decrease, and then this is the actual amount. The y-intercept, same thing. What happens when you plug in 0 for x right here, it just wipes out this term altogether. So our y-intercept is this whole number right here, 18,773. And that represents at 0 miles driven because the x value that I plugged in 0 for represents miles driven. So when I plug in 0 for x, at 0 miles driven, which in this case means a brand new car, we predict the price to be about $18,773. If you're looking at this number and trying to figure out why it's not matching up with right here, out of curiosity, I thought that too, but look at where it starts. This number would be 10. So technically when I plug in 0, this line would continue a little bit, so it would be pretty close to 19. So careful, for some reason they didn't start this on the x value, but if you were confused about that, just keep that in mind. Okay, and so for this next problem, it's still talking about used Hondas. This is all still the same data. We're still using all of these dots and this information here. The number of miles in thousands for the 11 Hondas that are on this graph up here. We're given the mean, the standard deviation, we have price mean, we have standard deviation of price. So we have an x and a y, mean and standard deviation, and they also gave us this r value. And from that, you have a bunch of equations that you filled out on your reading guide, but we can actually come up with the equation of the LSRL ourselves, just given the information that's in this problem. So I'm going to show you that and work through the formulas really quickly, and I'm going to first write out these numbers labeled clearly that were given in the problem. Okay, so I have all 5 pieces of information that we were given. Careful and make sure that you're labeling clearly which one's the x, which one's the y. Remember, the x is always the explanatory. So what explains what? The number of miles explains the prices. So the x is the miles and the y is the prices. That part does matter. And I've got my r value that was given right here last. So the first thing, and this is a formula that you have written down to find the b in the y equals mx plus b. So first of all, you take your r, and then you just multiply it by sy over sx. And so remember, these represent standard deviations, and in order to remember which one's supposed to go on top, it's just like slope, y over x, so same kind of thing. So that work is going to look like this. I have negative 0.874 times 1899. I'm just pulling the numbers from my list over on the left, 19.3. And that gives me a grand total of negative 85.9962, which you can see is pretty close to negative 86, which we were given in the original problem. So I'm just trying to make sure that it's matching up with what I have up here. So off slightly due to rounding errors. Otherwise, that is the formula and how we're going to get that one. So second thing we need to do is find A. And our formula for A is y bar, or the mean of the y's, equals A plus B x bar. And we're given a bunch of those numbers also, so again, we're just going to plug in. And what that's going to look like is my y bar is 14225. I don't know the A, but I did just find the B. I'm going to use the negative 85.9962. You don't want to round until the very end, just so that we're not losing some points for inaccuracy here. So I'm using the decimal form. And again, this number is just this one. So you do need to use like the answer for the first part in order to get the second part. When you solve that number, we get A equals 18,767.798, which again is very close to what we were given up here, 18,773, 18,767. The reason that those are a little bit off is just due to rounding errors. And so that tells us we now have our A and our B, so now I can write my equation for my LSRL. So that means my y hat, remember that means my predicted price, in this case because the y is representing price, is 18,767 point, I'll round to 80, minus, and I have 85.9962x. That's my LSRL using those two numbers that I came up with, A and B. One quick thing as a reminder, just as an FYI, these formulas you don't need to have memorized. They are on the formula sheet. So you'll be given this and this. So that's good. You just need to know kind of like where to plug the numbers, what to do, whatever. Okay? So let's flip the page, go to the next problem. We are still the same data, and here we have the all individual values. What I'm going to do is copy the LSRL, and then we're going to kind of walk through this residual stuff and talk some more about residuals. We have a residual plot down here that has to do with our original data. This is the same graph as it was on the front page. So this is the equation that we were given for the original problem, so I'm kind of using the one we were given and not the one we calculated because there were so many decimals there, just a little bit easier to write the one we were given. But it asked me to first verify the residual plot by taking the first data point in the scatter plot, which is this one, and calculating the residual. So all we're doing here is we're taking our x value of 22, and what this data point represents right here, the 17,998, that is the actual price that the car was sold for with 22,000 miles on it. And remember that this y hat is just our predicted price. So it's going to differ probably from this number a little bit. And let's figure out, first of all, how much it differs by. So the way I'm going to do that is I'm going to take my 18,773 minus 8616, plug in 22. And this is going to give me an answer of 16,877.5. And as you can tell, that differs from the price that the car was actually sold for. Good for the salesman for selling it for a lot more than what we predicted. And so what I'm going to do there is, in order to calculate the residual, we have a formula for that. The residual is the observed minus the expected. And so the observed means from the table, or the actual value, the actual price that it was sold for. The expected one is the y hat. And so that is the order that you always subtract them in, because a negative residual is really important to differentiate between a positive residual. So it's always observed minus expected. And so my observed value from the table up at the top is that 17,998. The expected value is this one that we just calculated. That was our predicted number, so 16877.5. And what that gives us is a residual of 1120.52. This is the residual. So really important that you understand how to calculate that number. And so let me go up to the graph now. And so for that very first dot in our graph, which is right here, that's the one that represents the 22,000 miles. And that dot is actually placed at 17,998, so you can see it's almost at 18. And the residual represents this distance here between the line, the LSRL, and the actual value. So you can see that that dot is above the line, meaning he sold it for more than we expected, and that's what a positive residual represents. So we have some values down here that are negative. That represents the salesperson sold it for less than what we predicted or expected. And so that is how to relay this information into the graph. And you can see that this residual for this very first car is represented right here. This is our residual plot. These are the residuals. So we have a graph of all of these residuals. I just showed you how to calculate one of them. So that very first one, again, at an X value of 22,000 miles. The residual, meaning, again, he sold this car for more than what we expected, was 1120.52. So I'm actually going to circle this and draw an arrow to that. And that is what that represents. So hopefully now you're a little bit more comfortable looking at a residual plot and being able to interpret what this information is telling us. So the last thing that we're going to do is we're going to continue on with a little bit more calculations. And so in this case, we have the sum of the squared residuals, which is abbreviated SSE, which is this huge number. But you also copied down some other formulas into your reading guide. One of them looks like this. The sum of the residuals, or the standard deviation, excuse me, of the residuals. That's what the S stands for. You have this weird formula. And so it's this SSE number, which, just in case you were curious, what that represents is the sum of all of the Y values subtracted by their predicted Y values and squared them. And so it's kind of like doing a standard deviation calculation for all of these Y values, taking the actual price of all the cars and subtracting from the predicted price of the car and then squaring them all and then adding them all up. That's what that number is. And that's what goes on top of our fraction in here, the 8499857. And then it's n minus 2 down here. You wrote that in your reading guide. That's part of the formula. And if you are curious why it's n minus 2 and not n minus 1 like first chapter that we talked about, you can read all about it in the book. But this calculation gives us 971.817. That is the, let me zoom out here, the standard deviation of the residuals. And then last thing we're asked to do is interpret. So I'm going to write out the sentence and then talk. So our interpretation for the standard deviation is very similar to the standard deviation interpretation from chapter 1. Again, this S here stands for standard deviation of the residuals. And so it's pretty much the same fill in the blank sentence for that interpretation. When we predict the prices of the used cars, remember to use your context. So we're predicting whatever the Y value is. And we're using our LSRL, our equation that we came up with, that y equals mx plus b, to make the predictions. Our predictions are off by about an average of this dollar amount. That is your interpretation for the standard deviation of the residuals. And so in order to find this coefficient of determination, which is another vocab word, this thing is the r squared. So remember, we've done a lot with r already. The coefficient of determination by definition is the r squared. So I can actually show you where that formula comes from as well. And so that, what you copied down in the reading guide, r squared equals 1 minus the standard deviation of the residuals over the total sum of the squared prediction errors, this SSE and SST. So SSE is from above, it's that 84, 99, whatever number. What I'm going to do is plug in those numbers for this formula, and then we will interpret that one as well, and then we'll be finished. So our SSE from above was 8499851, and the SST we were given also 360740. So a big number. And what is this SST, you might be wondering, and how does it differ from the SSE that we did earlier? Oops. This SST right here is almost the same thing. It represents a sum also, but instead of taking the predicted values, we're taking the mean of all the y's. So very similar, but a key important difference. So compare this, which is the total sum, and compare this to just the standard deviation, comparing it to the prediction error. So that's those two numbers, where they come from. But when I calculate this number, it gives me my r squared, 0.764. And remember, that's the r squared. And so you would square root that number to find the r, and that would tell you how closely all those dots fall to the line, for more or less. I'm going to write out the interpretation. And so just to finish up, here is our interpretation of the r squared value. So you already know that the r value comes from the r squared, you just square root it. But you can turn that number into a percent, and what it represents is the variation in the y value that's explained by the linear relationship with the x value. And so I'm just always adding context whenever possible into these, which is why I underlined in blue what would change depending on the question. But you're taking your r value, it's a percent, and then explains the variation in the y value. So, you know, those y values didn't all fall perfectly on that line. There was some variation. And 76.4% of that is explained by the linear relationship with the number of miles driven. So there's also other stuff that goes into the price of used cars. Our r squared value is not 100% because you can't explain the price of 100% of the cars based on miles driven. There's other stuff that plays into it. Maybe was the car in an accident? Maybe how many years old is the car? What is the transmission like? What are the tires like? All kinds of other stuff plays into it. But 76.4% of the variation is explained by the linear relationship, just taking into account number of miles driven. That's all for today. Bring your questions tomorrow. Thanks for watching.